Okay, so question 2, we've got a question around the specific heat capacity of water. And we'll look at what this means, and it tells us we've got a joule meter. So this is put in, that's the energy in. We're putting some electrical energy in. That's going to a heater to give us some heat energy, and then we're trapping that heat energy in water. And we know that the specific heat capacity of water is 4 joules per gram degree C. So all that means is if I had 1 gram, which is 1 centimeters cubed of water, I would need 4.2 joules to increase that by 1 degree C. Now, all substances, or as far as I'm aware, most substances, scientists have worked out this value. So for an example, I'd need to put more in it. So you can imagine if I've got, say, let's do a cloud, some air, and if I've got a chunk of metal, if I was to put the same amount of energy into it, in this one, the temperature will only go up a small amount. In this one, the temperature will go up more because metal's a good conductor. So it says state the measurements needed to calculate specific heat capacity. Well, specific heat capacity of water, what we're going to need to do for that, the value for that is C. We're going to need the equation Q equals M times C times the change in temperature. So if I want to work this out, the things that I need to know, and let me just change the colour, are I need to know the energy I put in, I need to know the mass of the water, and we've just said that 1 kilogram equals 1 litre of water, or 1,000 centimetres cubed, and we need to know the temperature change, and that's it. And we could rearrange this so that C equals the energy I put in divided by the mass of the water multiplied by the temperature change. So model answer, we're going to use Q equals MC delta T. We're going to talk about each of these bits. So the first part, we're going to need the volume or the mass of the water. And I've said I'm going to measure the volume with a measuring cylinder or get the mass of the water using a balance because it doesn't tell us how much is in that pot. Next one, we're going to need the temperature at the start and at the end. And I'm going to use the thermometer because it's giving me clues as to what to do. And then the next part is I'm going to need the energy input from the joule meter. And that's because if I know that C equals Q over M delta T, I need to know each of those bits. And again, that will be taught later on this year. Next one, state 2 ways that the apparatus could be adapted to improve the procedure. So here's that picture again. And what we can see is, well, I'm going to put some heat energy in, but there's some really big problems here. First one, we're using a normal thermometer. I can change that for a digital thermometer. That'll get me a mark. I'm using a polystyrene cup, but even better would be to put some more insulation around the outside because I'm putting heat energy in. I want that all to stay in the water. So I want to try and stop the heat energy dissipating into the surroundings. And then the 2 ones that I'm going to talk about are, well, oops. This heater isn't fully in the water. I've got a great big gap there. So that's heating the air. That's not great. And the other part is, as you'll see when you do this practical, I'm going to have to add a lid. Otherwise, when I heat the water, it's going to evaporate. And as it evaporates, it'll take some of the heat energy out. Because the crucial part is, I want to put heat energy in and I want it in that water. So the 2 answers I've gone for, add a lid to prevent thermal energy dissipation through convection, through evaporation, into the air. And then the last part is ensure the heater is fully submerged in the water. But as I said, I could have gone in there, swapped the thermometer for a digital thermometer connected to a data logger, and I could also have gone for add more insulation around the polystyrene cup to get more heat energy into the cup. Next one, this is a tricky question actually. It's a bit of a trick. Got a graph, predict the temperature if the heating continues up to 8 minutes. But the crucial part is it says predict the temperature of the water. So go along there. Here's 8 minutes and I can see, and what it's going to try to do is it's going to try and trick you into picking 105 degrees C. Well, the crucial part is this is water and you need to know that its boiling point is 100 degrees C. So it's a nasty trick, a nasty question. Next one. Another student tries to melt some ice. The student melts 380 grams of ice. I'm going to underline that. The specific latent heat of fusion is 3.4, and I can see that that's joules per kilogram. So instantly I'm going to change that into kilograms, 0.38. And it says calculate the thermal energy needed to melt the ice. So we need to use the formula my quirky llama. The heat energy I need to melt or to boil a substance is whatever its mass is times some value that scientists have worked out. So it says calculate the thermal energy needed. It's nice, really. As soon as we make that change for the grams, we're good to go. Q equals ml, which you would have picked from your formula sheet. So I just need the 0.38 times 3.34 times 10 to the power of 5, and then I get my answer 1.27 times 10 to the 5. And that's that question done.